talk about how to figure out the numerator for partial fractions. I'm going to start with, well, we'll just start with something that has quite a complicated denominator, and then we'll figure out what has to be, or what fractions this could be decomposed into. So I'm going to start with, like, this could be x plus 1 squared, and so x squared plus 1 squared times x to the fourth plus 1. That might be a good example. Okay, so when you're trying to figure out what's going to go on the right-hand side of the equals, in other words, what fractions are you trying to decompose this giant fraction into, you need to look at your linear factors here. And by linear, I mean x plus 1 is the x is to the first power. So that's considered a linear factor. This x squared plus 1, that's considered a quadratic factor. And this x to the fourth plus 1, this is a fourth degree factor, I guess is what you would call that, or a fourth degree polynomial. Okay, so for linear factors, we're going to say it's going to be just some constant value over that, plus, because there's a multiplicity of 2, this could be something over x plus 1 squared. Okay, so we've kind of taken care of the linear factor. Now I'm going to look at this quadratic factor. This is a little more interesting. So if you have a quadratic factor, in other words, your x is a power of 2 in the factor, then you're going to need to have a linear term and a constant. So for x squared plus 1, you need an x term and a constant. So that's going to be a cx plus d. And then because there's a multiplicity of 2, we have to include the x squared plus 1 squared term, and that's going to be 2 more constants, right? We need a x term plus a constant. And now if we have an x to the fourth, for a fourth degree denominator, that means we need a third degree polynomial on the top of our fraction. So that's going to be something times an x cubed plus something times an x squared plus something times an x plus a constant. So since we've already used a, b, c, and d, it'll have to be g x cubed h x squared. I'm not going to use I because it looks like a 1, so j times x plus a constant. And that is how you break down this denominator right here. Okay, so I might do one more example, just so you get the gist of it. Oh, and before I erase all of this, basically, you're going to take a look at the factor, or the potential denominator that you're trying to separate, and you're going to put a term on top in the numerator that is of a degree that is 1 less than the denominator. So this factor is a first degree polynomial. So on top you have a 0-degree polynomial. And a 0-degree polynomial is just a number. It's just a constant. 3 or 10 or 1/2. These are all 0-degree polynomials. Okay, again, this factor here, x plus 1, first degree. So that means up here, we need a 0th degree polynomial. This one is a second degree polynomial. So then on top, you need a first degree polynomial, which is just a linear term. Okay, and then here, second degree polynomial in the denominator. So you need a first degree polynomial in the numerator. And right here, we have a fourth degree polynomial in the denominator. So we needed a third degree polynomial in the numerator. I'm not going to explain why this is the case. Actually, I can't remember right now. It has something to do with whenever you long divide the original polynomial, the remainder for a nth degree polynomial could be a n-1 degree polynomial. But we might get into that later. It's actually irrelevant. All you need to know is that whatever you have in your denominator, you need one less degree in the numerator. Okay, so I'm just going to do one more example really quick. I'm going to erase this. And I'll just make up something for my numerator. And then I'll say this is going to be x to the fourth minus 1 Okay, so this one is going to be a little different because the factors are not obvious. In the example before, the denominator was completely factored as much as it could have been. But now, there's some things in our denominator that are not factored completely. In other words, our factors are not prime. So we're going to go ahead and factor those first. The first thing I'm noticing is that this thing can be factored. X to the fourth minus 1 is like the difference of two squares. So this is going to turn into x squared plus 1 times x squared minus 1. And actually, this can be factored again. So I'll get to that in a minute. Now I'm noticing that this one here, the x squared term, has two linear factors. It could be x plus 3 times x plus 2. And then x to the fourth plus 1, just like in the last example, this is actually already prime. It cannot be factored, so we're just going to leave it as is. It's just a fourth degree denominator, which is kind of unfortunate, but we're just going to leave it like that. Okay, finally, this underlined piece here can be factored a little further. So write what I have. X squared plus 1 is prime. X squared minus 1 can turn into x plus 1 times x minus 1. And then we have x plus 3. And then we have x plus 2. And then we have x to the fourth plus 1. Okay. And our numerator actually hasn't changed. Okay, so now I'm going to take this piece that I have a box around, and I'm going to figure out exactly how many fractions and what those fractions might look like if we were to decompose this. So I'm going to erase this a little bit and just start writing the potential factors of this fraction. Okay, so it could be something over x squared plus 1. And like I said in the previous example, if you have a quadratic factor in the denominator right here, you need a first degree polynomial in the numerator. So that's going to be like an ax plus a b, right? We need an x to the first term, and we need a constant, an x to the 0. Okay? And then it could be something over x plus 1. And this is already a first degree, so up top we have a 0th degree. This is a first degree because this is a second degree. This is a first, so this is a 0. Okay, and then we have something over x minus 1. Again, this is a first degree polynomial, so you need just a constant term up top. And then same thing for x plus 3. You need a constant over x plus 3 because it's a linear term. And then a constant over x plus 2 for the same reason. And then we get to this weird x to the 4th denominator. So x to the 4th plus 1. This is a 4th degree polynomial. So on the top we need a 3rd degree polynomial. And that's going to have to be g times x cubed plus h times x squared, j times x plus constant. Now, notice when I have these higher degree polynomials, you have to include constants for every possible power of x, starting at 3, and then we need 1 for 2, 1 for x to the 1st, and then you need a constant. So a 3rd degree polynomial, like this one here, has 4 possible constants that you will have to solve for. Now it may turn out some of these are equal to 0, but you have to assume that they might be there. So go ahead and put letters for them and solve it as if they existed. You might find out that they're equal to 0, but you need to account for them. That's going to be the end of the video, and I may upload another one later if this is for some reason unclear. Yeah, so let me know if you have any questions.